All right, welcome to video 7. In this video 7, we're going to be diving into problems that involve modeling using trigonometric functions. So essentially what we're going to be looking at are applications and word problems. We'll be diving in a little bit into given information, again, how do I write the equation for it? And then you'll have a two practice sets, actually one specifically with modeling that has like 8 to 10 examples for you to go through and try. I would encourage you to pick at least two to go through and do. And then you'll have another practice that'll be a little bit similar to just basic, given a function, can you tell me about the transformations and amplitude and period, etc. And then given a graph, could you write the equation and tell me amplitude, etc. So this video will help with that. The previous video is kind of the primary one for that. This one we're going to be diving into a little bit more of word problems and how can I decipher that information. All right, so just to begin, let's look back at the general graphing form of sine. You'll kind of see in the video, I've got, this is a graph taken from the CPM book, where we can go through and kind of help figure out like what the letters specifically are referring to, so you have a picture to go along with what I'm about to write. All right, now the general graphing form for sine specifically is y is equal to a sine b parentheses x minus h plus k. All right, now I'm going to use capital letters for a and b, and then lowercase everywhere else, so that's really the only difference here you'll see in the graph. The a, I'm going to go ahead and refer to as the absolute value of a, yields the amplitude. This again is the height or depth of the wave. Think about this as the length to the max or min from the midline. So here in the graph, you'll see this marked off here with the lowercase a. I'll use a capital. And here, this distance is always equal. Now, the reason for the absolute values, and this is something that I didn't hit on very much in the previous video, and that we'll actually use in the first example, is that your function can technically be negative. So for example, if I was to give you something like negative 3 sine of blah, 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 what this negative is doing, remember, is flipping your graph. So instead of sine, which generally starts in the middle and then goes up, this negative is telling me that I'm going to instead still start in the middle, but now travel down. The 3 is still dictating the length to the max or min from the starting point. So no matter which direction I go, we're still only going to travel 3 units. And thus why in the true definition, you see an absolute value, because again, it's the number that matters, not the sign. So make sure when you give your amplitude, you're always given the positive value. And then if you were asked to sketch or look at the graph, make sure you're using a negative when appropriate. And again, I'll show you an example of that when we get to example 1. All right, for now, I'm going to kind of clear this off. Because I'm going to move to the next part here, just going from left to right in my definition, which is B. B stands for the angular frequency. This is the number of complete cycles in a normal period of 2 pi. So this means by definition, then period, which I'm going to abbreviate as P, is equal to 2 pi divided by B. 2 pi divided by your speed or how frequently you're completing your cycles. This establishes another essential relationship where P times B is always going to be equal to 2 pi. Notice that's just cross multiplying the B over. And this yields another helpful formula where frequency is always 2 pi then divided by P, your period. Now, graphically speaking, we can see the period marked off here. It is the length of one complete cycle. So how long in terms of x values or time does it take for the graph to go up to its max, down to its min, and back to the middle? and I just did this in the air. I'll kind of show you again. This counts as one period, and then I'm going to hit another period, and that'll be the same measurement. Same thing if I was to travel to the left. This would take the same amount of length, horizontal distance there. All right, and so there's period. Period again is based off of frequency, and we can find it based off of that. All right, now the next thing, I'm actually going to skip over h for now. I'm going to look at k. All right, k is the vertical shift, but specifically it is the midline, or average between the max and min, which hopefully makes sense. I'll say maximum and minimum, which hopefully should make sense again, because if this is the vertical shift, which is representing the middle of the graph, then it should be the average. It should be the direct middle between the highest point and the lowest point, and that's where you'll see again on this graph. You'll see the letter K being represented here, where this first point is located, but it doesn't matter where we are. That midline is always a distance of K from the origin, from the x-axis. And if K is negative, then that would mean that your average is then below the x-axis. If your K is positive, like in this example, you would be above. All right, now, I told you I was going to hold off on the h. I'm going to talk about the h right now. And I'm going to put it here on the side because the h really depends on if we're modeling with sine or cosine. Now, because we're modeling with sine in this example, no matter what, h represents your starting point. It is your horizontal shift, which is your starting x value. It's where we're going to start drawing the graph. And this is where it matters in terms of sine and cosine, because for sine, when I start at h, I'm actually going to start in the middle. Or think about it like the crosshairs of where h and k intersect. That point right there is like my new origin. That's where sine is going to begin. And I'll either travel up if I have a positive a, or I'll travel down if I have a negative a. Now for cosine, this is really the only difference between sine and cosine. Cosine starts at its max. So when I do my horizontal shift and I travel h to the right or left, instead of starting in the middle, I would actually begin at its maximum point. So if I was looking at this graph here, where they have essentially h marked off, if this graph was supposed to be for cosine, this wouldn't be my h. I'm just going to kind of get rid of it. Because for cosine, what I would need to do is locate where my maximum is, which is here. And this x value, whatever value number that is, that would then represent my h. Because for cosine, that's where I would start and mark this thing off. Now, if I had a negative a, then I wouldn't be starting at my max, but I would be starting at my min, because it is a flip. And so then what I could do for h, if I wanted to use a negative cosine function, is I would go and say, okay, well, when am I at my min? And then this would be my h in terms of its measurement. And again, we'll look at this in the next example. All right, but this is the basics. It's always true. Essentially, no matter what, if it's sine or cosine, amplitude, frequency, and vertical shift, and my h, all are defined the same way. When we are modeling, my h depends on if I want to start in the middle and use sine, or start at the max and use cosine. All right, but it's all about my starting point. All right, so let's take a look at example 1. And I've got some questions to kind of help guide us. All right, Jesse wants to represent the height of a yo-yo over time by using a trigonometric function. He starts timing the yo-yo when it is at its lowest point, which is 5 inches above the ground. All right, and so going ahead and taking a look at this graph, notice that at 0, like when this clock is about to start running, this yo-yo is at its lowest height. So now imagine Jojo is actually like standing like right here, and he's playing with this yo-yo. He's starting the timer and he's measuring it based off the height from the ground. All right, that's probably the biggest thing to kind of notice here. All right, now the string length is 30 inches, and it takes 2.5 seconds to return to the same position. All right, so the graph at the right, let me get rid of my really crappy Jesse picture. The graph at the right represents the path of the yo-yo. Explain why it has a peak at 35 inches. In other words, notice the maximum here is at 35. Well, why is it 35 if the string length is 30? Well, the reasoning is if the lowest point, if the min is at 5 inches above the ground, and the string length is 30, when it comes back up to his hand, it's going to travel another 30 inches, but it's going to increase by 30. So that means the max, the peak, has to be at 5 plus 30, which is 35 inches. Oh, sorry, I put that in the wrong spot. This goes up here for A. All right, so that's why it has a peak at 35 inches. All right, so what about part B? What is the amplitude of the function? All right, in order to find amplitude here, I'm going to do something that I talked about in the previous video. And this is a technique that we'll use when we get into more of the word problems, and it'll be an easier way to approach it. I know that amplitude is essentially the same, and it's measured from the midline. Well, what that means then is between the max and the min, I'm going a length of 2a, two of my amplitudes. So for example here, then, if I find my max, which is 35, and I find my min, which is 5, that means that the difference between these two, in this case 30, has to be equal to twice my amplitude. So this is telling me that my amplitude, my A value here, has to be 15. Units would be 15 inches. And I can see this by going to the graph, because I even told you in the previous video, a lot of the times when you have the graph, it's really easy to find the midline because you're literally cutting the graph in half. So I would say that the midline is probably 20, which means that if I was to mark off my amplitude, the amplitude is here and the amplitude is here. Notice then that by definition, I have 2a is equal to 35 minus 5, the difference in height here. And so we essentially then have a basic definition in terms of finding the amplitude. The amplitude is always half of the difference between my max and my min. So I can always take my max, subtract my min from that, divide by 2. That will always tell me what my amplitude is. And so in this problem, that'll be 15. All right, well, what about the vertical shift? Well, remember that vertical shift is represented in a trig function by that midline, by its average between the max and the min. So say again we didn't have the graph. If I wanted to find the vertical shift, I would need to find the average between the max and the min. Where is that middle ground? Well, to find the average then, this time I would do 35 plus 5 and then divide by 2. This gives me 40 over 2, which is 20, which if I look at my graph, there's my midline. That represents my k value. So now determine the period of the function. Use this to find the value of b, which is called the angular frequency for the graph. Period is always easier to find than b, especially in a word problem, because remember what period is referring to. Period is defined as the length of time, the length of x, or whatever, in this case, the length of time, to complete one cycle. Well, when you're doing a yo-yo, what constitutes one cycle? Well, you can measure it in two different ways, and really multiple ways, but the two easiest would say, all right, well, one cycle would be letting the yo-yo go, it hits the min, and then comes back to my hand. So in other words, how long does it take for the yo-yo to go all the way down and then come all the way back up? Well, for us, he's starting the time in between, he's starting the time when it gets to its lowest point. So one cycle for him would be from the lowest point back to his hand and then back to its lowest point. So asking the question of determining the period is really trying to determine, well, how long does it take for it to go to the same position? Well, we're actually given that in the problem. In the problem, we are told it takes 2.5 seconds to return to the same position. And we can even see that graphically because I'm at the lowest position at 0, and it takes exactly 2.5 seconds to get to the lowest point again. This is marking off the period in this problem. So the period P is 2.5. Now, I gave a formula to find B earlier. We know, again, just to present this, that P times B has to be equal to 2 pi. So if I want to find B, then I'm going to do 2 pi divided by my period. Well, the period in this case is 2.5 seconds. And so 2 pi divided by 2.5. I'm going to try and do this in terms of maintaining a fraction, just so it's nice and easy to kind of look at. If I do 2 divided by 2, so in other words, like I don't want to use pi, like in my calculations, I want to leave pi as pi and leave it as a symbol. So if I want to do 2 divided by 2.5, this would be 2, kind of running out of space. This would be 2 divided by 5 over 2. That'd be the fraction equivalent. So 2 pi times the reciprocal, 2 over 5, would be 4 pi over 5. So if you were to do 2 divided by 2.5 in your calculator, you should get a decimal that's 4/5 or 0.8, if I'm doing that right in my head. And then pi would just be pi. So again, when you're doing something like this, especially in a problem that doesn't involve pi, like when we have time, try to get exact answers for my frequency. And we want pi to be in that final answer. That's perfectly fine when I'm going through and finding my B. Okay, now, this is what I was referring to in part E when we were going through and doing the general stuff. So I'm going to go through and kind of clear off my graph here. I just want to clear, there we go, and just get rid of all that other stuff. Because in part E, it's going to ask this question. The graph can be represented without utilizing a horizontal shift. Which trigonometric function can be used then as a basis for this graph? All right, and I kind of just want to run through our two options. All right, because our two options are using sine or cosine. And that should be hopefully kind of obvious because those are the only two functions that we talked about. Now, sine again starts in the middle. So if I want to use sine as my function for modeling, then I need to look at the midline and not only find where am I in the middle, but I need to find when I'm in the middle and the graph is now going up as I travel from left to right. And so one of the first markers that I could find here would be right here. The issue with this is that this point right here is not easily defined. I don't know what this is. Right? If I go here, I still don't really know what that is. Here, I don't know what that is. Here, I don't know what that is. In other words, these values are not exact. Cosine, though, starts at its max. So what I could do is instead look at my maximum and say, okay, can I find this? If I can, then this can be my H value, whatever that maximum is. I'm trying to get this to sit still. There we go. Ooh, there. It's not great, but we'll do it. So notice even here, like that's not exact. Now we could make a very, very good educated guess as far as what that value is, but notice again how it's not going to be super helpful. Well, the other thing about cosine that's nice is that remember, if I negate the original function, it's going to flip it. So instead of it saying starting at its max, I could look for when I'm starting at its minimum, and then that would be my H value. And so in this kind of problem, this is why it says I don't really need a horizontal shift, because remember that the clock is starting when I'm at my min. And so in this kind of case, my H would be 0. but it's only 0 if I use cosine and I negate the function. So whatever my a is, it needs to be negative when I write out my equation. Now the reason why that I don't worry about this with sine is, remember that when I'm in the middle, sine is equal to 0. So even if I negate the original function, it doesn't really change what h would be, because h would always still be here in the center. Versus with cosine, I'm actually really looking at two different values between here and here. Notice even at this minimum, I know the exact value. So generally speaking, when I'm modeling, I normally only use cosine when I'm modeling, because it's so much easier to determine when I'm at my max or my min. But sometimes your graph, it will be easier to see when I'm in my middle, and I'll be given that exact value, and then I could use sine. Now, there are cases where I'm able to do both, and then we could write the equation for both. Either answer would be appropriate when I'm going through and modeling. All right, for now, we've got my h. I know that the requirement here for h is that I'm going to use cosine, and my a has to be negative. So let's go through and write out the equation for this. So the height at time t, so I'm going to use h for this, is equal to negative, well, my amplitude was 15. I have to use cosine. B was 4 pi over 5. Then I have parentheses, t, since I'm dealing with time, minus 0, that was my h. And then my k is positive 20. Here is the function, here is the equation that would model the height of this yo-yo over time. Now, in all of the modeling questions that we're going to do, the first part is really just trying to find what that model is, and that's where a major chunk of your points will come from when it comes to an assessment. The next thing to do is now apply that. So, okay, we've got the model. Now, how can I answer questions, or how can I use that model? So determine the first 4 times when the yo-yo is 25 inches above the ground. In other words, when the height is 25, what's time? And not only that, I want the first 4 times. So we need to figure out how to answer this question. In other words, if I set my model equal to 25, can I figure out what time is? And we haven't solved any equations like this. That's actually what we're going to do after we model. So for now, the only way that I can really go through and solve this is by using a graph. And so I'm going to go to Desmos. Okay, I'm going to put in my model. So the model again was negative 15 function cosine. We had 4 pi divided by 5, parentheses, x minus 0, close parentheses, and then this was plus 20. Now if we look up here, I'm going to kind of change the scale so we can kind of see. We can even stretch it out a little bit, make it look a little bit closer to the problem. All right, and then what I want to do is I want to figure out, well, where is this 25? Well, one of the nice convenient things that I can do with this in Desmos is I'm essentially saying, where is y equal to 25, and where would these functions intersect? And again, if I'm looking for the first 4 terms, I'm looking for, or times, I'm looking for after 0. So starting at the lowest point here, the first 4 times would be here, 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 and here. So those times are the x values. So that would be 0.76, 1.74, 3.26, and 4.24. Now, notice that I really only need the first 2 times. Well, no, sorry. I'm not even going to. Yeah, I really only need the first 2 times. Never mind, I will answer this question. All right, and so let's say 0.76 and 1.74. So the first two, 0.76, that's T1, and 1.74. Well, remember that we found the period. the time it takes to get back to the same exact spot. So if 0.76 works, then the next one can be found by adding the period to that. Well, the period was 2.5 seconds. So if I go 0.76 plus 2.5, I get 3.26. If I go through and I add 2.5 to 1.74, I get 4.24. Well, let's double check on the graph again. Let's see if these 2 points were actually right, because I already forgot. 3.26 and 4.24. We're at 25 again. So once I find these 2 points here and here, we can actually find every other value as long as we know what the period is. All right, so this is kind of the first example that looks at an application type. All right, now in example 2, what I want to do is I kind of want to focus on how we write. And I was going to scoot this down just a little bit. How we write in the equation and why we need the parentheses specifically. So here's the problem. So write the equation of a sine function that has a graph with a period of 2 pi over 3 and a horizontal shift of pi over 2. All right, well, again, if I want to write the equation for sine, I'm just going to write it here in terms of, like, let's assume that amplitude is 1 and that there is no vertical shift. So k is equal to 0. Then I need to know what is b and what is h. All right, well, the period is 2 pi over 3. And I know b is equal to 2 pi over the period. So 2 pi divided by 2 pi over 3. This would come out to be 3. So there's my angular frequency. My h is given. I have a horizontal shift of pi over 2 units to the right. So it'd be pi over 2. All right, now you'll notice I have 2 different names here because there could be potentially 2 ways to write this. Laurel comes in and writes it like this. She says that the equation would be sine of 3 parentheses x minus pi over 2. This is how we've been writing it so far with the parentheses on the inside. Hardy comes in and wants to write it like this, 3x minus pi over 2. In other words, what if you don't put in the parentheses here? Because this still looks like I'm having a horizontal stretch or compression by 3, and I'm still moving at pi over 2 to the right. And what I want you to notice is that if we were to take Hardy's answer here, and I was to actually go through and make it look like Laurel's, I would need to factor out that 3, and I'd be left with an x minus pi over 6. So that the h in Hardy's problem is actually not pi over 2. We're not getting the appropriate horizontal shift. To show you this visually, I'm going to go back to Desmos and let's clear off what we have here. Again, I'm looking at a graph of sine where specifically I want to do 3 parentheses x minus, and I want to do pi divided by 2. I'll go back home so we can see it. Now, Hardy wants to do sine of 3x minus pi over 2. Now you can see that these graphs are completely different. Green, again, is Laurel's, which is the appropriate way to write it. Hardy's is in purple. Now, it's kind of hard to tell right now because I don't have the radian measures up. So again, to get the pi's on the x-axis, click on the wrench. I'll do the projector mode so it's easier to see. And then under x-axis, go to step. And if you're just to put in a pi, you'll easily see the pi here. So let's see if I can get, there's pi over 2. All right, and so let's get rid of the purple one for now. So we can see that, again, Laurel's is the correct graph because here at pi over 2, I'm starting in the middle. So there's the correct horizontal shift from 0. The graph goes up, down, and back and returns by 7 pi over 6. Now, if I zoom out, though, to where I can see 2 pi, count the number of cycles we would have, count the number of crests, maximums, that we have by the time we get to 2 pi. Well, I get 1, 2, 3, and remember 3 was my angular frequency, which is how many cycles I should get within 1, 2 pi. So this matches the definitions that we got before. It matches what I want in the problem. Now, if we were to look at Hardy's work, and if I did not include the extra parentheses, notice that this graph starts in the middle at pi over 6. And if I was to go to 2 pi over 3, I still get the correct angular frequency, but again, the shift is wrong. I'm not shifting it far enough, or according to at least what I want. So the extra parentheses is very, 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 very important. And it's due to the way that the order of operations works, etc. Algebraically, to show this one more time, remember that generally x starts at 0. And so if I was to go through and set each inside piece here equal to 0, I should see x be translated to the new horizontal, which is pi over 2, horizontal shift, new starting x value. So if I do 3x minus pi over 2 and set this equal to 0, I would divide by 3 first, and then I would need to add pi over 2, which gives me just pi over 2. Well, that works. But if I do this x is equal to 0 thing for Hardy's, notice I would not divide by 3 first. I would add pi over 2 first. Then I would divide by 3, which gives me the starting x coordinate of pi over 6. And so it's because of, again, how this is written, we need the extra parentheses. And so I highly encourage you, make sure you're writing these in when you're writing the main equation. Otherwise, you will screw up your starting value. All right, so example 3. The graph of y is equal to sine of x is stretched vertically by a factor of 2, makes 3 complete cycles in an interval of 2 pi. It is shifted up 4 units and shifted to the right pi units. Write the equation of the transformed function. All right, so we know the general definition. We have our information. All right, so it is stretched vertically by a factor of 2. That is my amplitude. It makes 3 complete cycles in an interval of 2 pi. That is my angular frequency. It is shifted up 4 units, so that is my midline, that's my k. And it is shifted to the right pi units, which is my h. So then, because it's a sine function, I know this has to be 2 sine 3, parentheses, x minus pi plus 4. It's as easy as that. You really need to know the formula, and then it's plug and chug from that point on. All right, example 4. So the graph of a sine function is shown below. So again, we're told specifically what type of function it is. State the amplitude, horizontal shift, vertical shift, and the period. Then B, write an equation using sine for this curve. This is a classic assessment style question that I would provide to you, whether you are tutoring, project, or if you're writing your own. I would expect to see at least one problem like this. All right, so let's go through. This is like the first example we did, except taking away the application aspect. All right, so state the amplitude. All right, well, amplitude, recall, is the difference between the highest point and the lowest point. So this would be -5 minus -1 divided by 2. So I'm going to do, let's see, well, I guess, let me rewrite this. So it's negative, because I said highest to lowest, so let me be consistent. So -1 minus -5, which would be -1 plus 5 over 2, which is 4 divided by 2, which is 2. The horizontal shift, if you notice this graph, it gives you a starting value here. That x value that's associated is pi over 2. So h is pi over 2. My vertical shift, which is k, is also the midline. And if I look at the graph here, the midline is at -3. And this is perfect because this should work with my amplitude of 2. So from -3, 2 steps up should get me to my max. 2 steps down should get me to my min. That checks out, so we're good to go. Also, the vertical shift can be the average between the max and the min. So if you were to go through and do -1 plus -5, and then divide this by 2, you'll see that we'll get -3. So 2 different methods to find that. All right, state the period. So the period is the length for one complete cycle. Well, we can do max to max. We can do middle to middle. We can do min to min. It really doesn't matter. I guess let's just do middle to middle since we're talking about sine, and I kind of want to maintain that sine is the middle in that language. It's also really nice because I know those exact x values. So I know that this distance here is pi over 2. This distance here is another pi over 2. So then the period is pi over 2 plus pi over 2, which is pi. All right, now if that's my period, now A doesn't ask for it, but because B is asking for my equation, I know that I'm going to need to know what my frequency is. And frequency is 2 pi divided by my period, which in this case is 2 pi divided by pi. So my frequency is 2. Now I can go through and write my equation. So I can go through and say that y is equal to my amplitude, which is 2, sine, frequency, which is also 2, parentheses x minus my h, which is pi over 2, close parentheses, and then minus 3 for my vertical shift. This graph is perfect because if I go to my starting x value, which is at pi over 2, the graph then goes up and then goes down, and I know it's going to come back up, pi units to the right. Here's my model. All right, so that is example 4. The last question, which is example 5, is going to show you, this is kind of the precursor for the practice, and will give you hopefully some directions into how to solve all of the modeling type problems. So use this as an essential example guidelines to walk through and do it. All right, so just to read through this, Burrell and Elaine always travel to Sunset Beach together for their summer vacation. Every year, they return to the same section of beach and spend their time around the pier. Elaine notices that the water rises and falls on the posts of the pier. She thinks that the height of the water can be modeled using a sinusoidal function. Now, this just means sine or cosine. Get ready because I'm going to start using this word a lot. Burrell is snorkeling and notices that the pier posts are slimy up to the lowest level of the tide, which is 2 feet for this particular post. Since Burrell and Elaine are always curious about the world around them on vacation, they have nothing better to do, apparently, and find out that there was a low point on the post at 8 a.m. and a high point 40 inches higher at 2 p.m. So good old Burrell and Elaine need to find better things to do at the beach, apparently. All right, so they're going to be working through this math problem to try and model this stuff. Bunch of nerds. So part A. Write an equation to model the height of the water relative to the post as a function of time, where t is equal to 0 will represent 12 o'clock midnight, and h of t will represent the height of the water in inches. All right, so we've got a picture here of her snorkeling, but I'm going to draw another picture down below just to help in terms of solving and kind of working through this and really just kind of help. I always encourage you to draw a picture as you do these word problems. So I'm just going to draw the post because that's what all of this is essentially measured off of. All right, and the very first thing that she's going to notice is that the water level drops to 2 feet above the ground or the sand or whatever, the ocean floor, because it remains slimy below that marker. So the water level will never drop below that on this particular post, meaning that this is going to be the minimum of the tide level or the height of the water. And we actually even know a time for this, I think, because they find out that there was a low point on the post at 8 a.m. So I know that when time is equal to 8, the water level should be 2 feet. All right, well, the problem also tells us then that a high point exists 40 inches higher than that low point. So notice that first off, this is in inches, but also that the 40 inches is not the actual max. The maximum is 40 inches higher than the minimum. Well, the minimum again was 2 feet, which is 24 inches. So then another 40 would put the maximum level for the water at 64 inches. And this would occur at 2 p.m. Now, when we're doing a graph and we're talking about time, my x-axis does not repeat after noon, right? So if midnight is my starting point, if t is equal to 0 is going to be 12 midnight, then 1 would be 1 a.m., 2 would be 2 a.m., 3 would be 3 a.m., etc., up until I got to 12. Well, then what would happen at 1 p.m.? That would be 13, 14 would be 2 p.m., 15 would be 3. Essentially, when we're modeling, we're always going to be using military time. So go ahead and when we're looking at a problem and you're going through and writing this out, convert everything in terms of military time. So when we say that it reaches its maximum at 2 p.m., I'm not actually going to use 2 as my t value for that max. I'm going to use 14 because that's the time value in terms of military or an integer, a real number, when this thing is at its max. I'm also going to want to make sure that I don't use feet because in part A, I'm told to model the height in terms of inches. So it actually works out that they told us 40 inches higher, and we went ahead and converted that minimum of 2 feet to 24. All right, so I'm just going to kind of write this away from the picture because, again, what I'm told now is I know that I have a max at 64 when t is equal to 14. I know I have a min of 24 when t is equal to 8. And then so looking at this problem, notice if we're thinking about time, the minimum would occur first, and then it's going to go to its max, and then the water is going to come back down to its min, and I essentially create a cycle or a circle here when you connect the tails. Well, how long does it take to complete one full cycle? In other words, how long does it take to go from 8 to 14 and then 14 back? Well, 8 to 14 is pretty easy to see. I can just subtract. This would take 6 hours. But if it takes 6 hours for it to go from min to max, if we're assuming that this is going to be symmetric and be a perfect circle, then it should take the same amount of time to go back to the min. So one cycle is 12 hours, which is nice because that's half a day. Well, this we just found is my period. My period is 12 hours. All right, well, in my model, though, I need to know what amplitude is. So what's amplitude? This is where that newish kind of formula I told you is really, really helpful. Remember that amplitude is always going to be my max minus my min, so finding that difference, and then dividing this by 2. So here, this would be 64 minus 24 divided by 2. This is 40 over 2, which is 20. There's my amplitude. All right, the next thing that I think is the easiest to find would be then B. So what's my frequency? Well, we know my period, and so we know that frequency is 2 pi divided by P. So I'm going to do 2 pi divided by 12. So this comes out to be pi over 6. All right, that leaves me now with my midline. So where's K? Now K is the average between the max and the min. But if I know the amplitude, then that means the middle has to be a difference of 20 in either direction. So that means 64 minus 20, the K has to be 44. Notice that 44 minus 20 is then 24, which is the min, or 20 plus 24 gives me back to my midline. I also know that this is the average. So if I go through and I do 64 plus 24 and divide by 2, we're going to get 44. All right, now I find all of these things first because my H, again, depends on if I'm going to model using sine or cosine. Now, I told you that cosine is always going to be the easiest, and here's why. I know that cosine will always start at its max, and that means then when I'm at my max is going to be my H value. And in a word problem like this, we're always going to be given the maximum, and I'm always going to be able to find when I'm there. So if I choose to use cosine as a model for this, then that means my H is 14, because that is when I'm at my max. So now my model, I could write it as H of t is equal to 20 cosine my B, which is pi over 6, times t minus 14 plus 44. Here's my answer to part A. Now to check this, what I could do is I could go to Desmos. Let's plug this in. All right, so I've got 20 cosine of pi divided by 6, parentheses, x minus, I've already forgot. What's my horizontal shift? 14. Close parentheses, plus 44. I'm not going to be able to see my graph right now, so I'm going to zoom out. There it is right there. And I'm going to get my x values to go back to being whole numbers since I'm looking at time. Perfect. All right, now if I check my max, I get a max at 2 a.m. and then 12 hours later at 14, which works because, again, I'm supposed to have a max at 14. Notice we have a min at 8, and then that would continue another 12 units and every 12 hours. So this graph checks out with what our model should be. All right, and so let's look at now part B and part C. All right, this is where we're actually going to use our model. I'm looking for what I did with my pencil because it seems to have found it. All right. Now, part B. At 11:30 a.m., the girls want to take a walk on the beach, but decide to wait until high tide. What was the height of the water at 11:30 a.m.? In other words, for B, I want to know what is H. I'll say what is H of t when t is 11:30. This would be 11.5. In other words, what is H of 11.5? Well, to find this, I just need to plug 11.5 into my model. So 20 cosine pi over 6, 11.5 minus 14 plus 44. Because this is not going to be exact angles, I have to use a calculator to approximate. When you use your calculator for this, we're using radians, so make sure you are in radians. And you could just take this and plug and chug. In Desmos, just to show you this trick, I'm really just trying to go through and find out when x is 11.5, what is my function value? So I can go through and say x is equal to 11.5. This will put a vertical there, and then I can look at the intersection. And so I know that the height of the water would be roughly 49.2 inches. Approximately 49.2 inches, which is a little over 4 feet. All right, and C. If this question is concerned about what's the height at a specific time, then the only other way I can ask a question would be, when am I at a certain height? All right, so in C, Braille's little brother Sean is 2 feet 7 inches tall. When is the first time after 8 a.m. that the water will be over his head if he plays right next to that post? All right, so in other words, I want to know when is the first time the height of the level will be at this height, because that'll be over his head, essentially. All right, well, this is feet and inches. So 2 feet is 24 plus 7. I'm essentially asking, what is t equal to when h of t is equal to 31? In equation form, this would be 31 is equal to 20 cosine of pi over 6 t minus 14 plus 44. And I want to solve this equation. For now, how we're going to solve this again is by turning to its graph, either by using Desmos or a graphing calculator. Here, I'm going to set y equal to 31, and I'm going to look for the first answer after 8. Well, remember, 8 is at this minimum, so that means I'm going to disregard this first answer here. The first answer is going to be 9.65. But I need to translate this because we don't think about time in terms of 0.65. In other words, this is 9 a.m. and it's roughly like 0.15 after a half. So this is probably something like 9:40. Well, how could I figure out what this would be exactly? Well, I can take that 0.65 and I can multiply that by 60 minutes. Because essentially I'm finding what is 65% of 60. If I was to do this in the calculator, I'm getting my calculator out on my phone because I've been lazy and I haven't gotten it out at all this video yet. 0.65 times 60 is 39. So really, really close guess right here. On the dot, it's about 9:39 a.m. So then that means by 9:40, this water would definitely be over his head. And hopefully he can swim. Otherwise, he would not be able to go out there. All right, and so all the problems will follow this mold. Where you'll be giving a word problem that's not going to be as long as this one, but will always kind of give you the same information. It will tell you when you're at a max, when you're at a min. It will either tell you the period or tell you something about the time it takes to go from one to the other. And then it's going to ask you, find a model, so write an equation, and then it's going to ask you to use that model, either what is the height or find something based off of an input, or based on an output, find the input. And in these kind of parts, we're going to be using that graph to go through and solve that. Let me know if you have any questions. I'll have answers posted, and the answers are actually posted under the normal lesson plans under 2.2 trigonometric functions if you scroll down. For now, make sure you take a look at both practice problems. If you have not worked on that project yet, work on the project. These problems here give you a really good setup to help answer the questions that I posted with that. If you haven't answered those questions yet, or if you want to go back and look and see how you answered those. Otherwise, hope you have a good rest of your day.